Hello there. In this video, we're going to primarily focus our attention on the idea of infinite products. We've already seen a couple examples where infinite products have a natural representation. For example, Somoza's quadratic recurrence constant, which is defined to be the square root of 1, square root of 2, square root of 3, square root of 4, and with infinite number of nested radicals here, can be expressed as an infinite product, namely the product from k is equal to 1 to infinity of 1 plus 1 over k to the power of 1 over 2 to the power of k. So, in addition to a couple of theorems associated with infinite products and their convergence, we're going to look at a couple examples on how to calculate infinite products, how to establish whether an infinite product converges or diverges, and also establish an intimate connection between infinite products, prime numbers, and the Riemann zeta function. To begin our discussion of infinite products, let's first consider a particular sequence. So we're going to assume that AK is a sequence of real numbers that is positive. And we're going to assume K is going to range from, say, 1, 2, 3, 4 to infinity. Some indexing set depends what you want. So the product from K is equal to 1 to infinity of AK can be expressed via natural logs and exponential functions, as we already know. So we know this is the same as the product from k is equal to 1 to infinity of e to the natural log of ak. This is where the assumption that ak is positive is extremely useful because we don't have to consider the complex nature of logarithms or exponentials. So what this is, we can express this as follows. So this is just e to the natural log of a1 times e to the natural log of a2 times e to the natural log of a3 times n infinite products, and so on. So what this is we can express this as a sum of exponents since we're multiplying exponential functions with the same base. So this is the same thing as e to the natural log of a1 plus the natural log of a2 plus the natural log of a3 plus and so on. So we can express this as e to the sum from k is equal to 1 to infinity of the natural log of ak. So under what conditions do we know that this product actually converges? Well, we already have a series of theorems associated with infinite series, therefore we can state the following expression. So, theorem. So the product from k is equal to 1 to infinity of ak with ak, a positive sequence, and k in the natural numbers, converges if and only if the sum from k is equal to 1 to infinity of the natural log of ak converges. And similarly, the product diverges if and only if the sum of the natural log of ak diverges as well. And that's very easy to prove, namely the product, so if the sum from k is equal to 1 to infinity of the natural log of ak is equal to alpha, and let's assume that this is a finite number, then the product from k is equal to 1 to infinity of ak, as we know, is already equal to the product from k is equal to 1 to infinity of e to the natural log of ak, which is again equal to e to the sum from k is equal to 1 to infinity of the natural log of ak. By definition, this is equal to alpha, so that means e to the alpha is going to be the limit of the infinite product. Alright, so let's go through an example. Let's consider the infinite product, the sum from k is equal to 1 to infinity of, let's do e to the 1 over k, let's do k squared. So 1 over k squared is the exponent here. So let's rewrite this out. So this is going to be equal to e to the 1 over 1 squared times e to the 1 over 2 squared times e to the 1 over 3 squared times and so on. So since these are same bases, we can add the exponents. So this is going to be e to the 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus and so on. So we can rewrite the exponent as a sum. So this is going to be the sum from k is equal to 1 to infinity of 1 over k squared. This is a p-series. Since the exponent is greater than 1, this definitely does converge. What does it converge to? Well, we should recognize this as e to the zeta of 2, which is a very important theorem that we'll prove eventually, namely e to the pi squared divided by 6. So in general, we can have the following theorem. So theorem, the product from k is equal to 1 to infinity of e to the 1 over ka is equal to e to the zeta of a. And this is going to be true for any a bigger than 1. There's a special product theorem. So let's do another example. Does the infinite product from k is equal to 1 to infinity of 1 minus 1 over k converge or diverge? Alright, so solution. So we know that this series is going to converge if and only if the sum from k is equal to 1 to infinity of the natural log of 1 minus 1 over k converges. So if this series diverges, then that product series also diverges as well. So what I'm going to do is I'm going to get a common denominator for these two fractions inside of here, so that we can rewrite this as the sum from k is equal to 1 to infinity of the natural log of k minus 1 divided by k. And I can split this natural log expression up into two natural logs. So this is going to be equal to the sum from k is equal to 1 to infinity of the natural log of k minus 1 minus the natural log of k. Alright, so what do we have here? So I'm going to evaluate the sum and see if we have any special relationships here. Because notice that this should be a telescoping sum. So we need to figure out, does this telescoping sum converge or diverge? We should be able to look at the first and last terms of that and see if that limit converges. So I'm going to plug in 1. So when I plug in 1, I get the natural log of 1 minus 1. So let's be careful how we rewrite that. So that's going to be the limit as k approaches 1 of the natural log of k minus 1. And let's approach 1 from the right-hand side. And let's see here. Minus natural log of 1, so that's going to be 0. So that's the first term. Then plus, let's do the second term. So let's plug in 2 now. So 2 minus 1 is going to be the natural log of 1 minus the natural log of 2. And then plus the next term. So when we plug in 3, we're going to have the natural log of 2 minus the natural log of 3. So the natural log of 3. And then plus all the way out to what? So once we go up to some arbitrarily large number, let's call it n. So that's going to be the natural log of n minus 1 minus the natural log of n. So that's going to be one term plus n, so on. So what do we have here? So natural log of 1 and 0 are going to cancel. Natural log of 2 and that term are going to cancel. This is going to cancel with the next term in the series. Let's call it there, or there actually. So this term will also cancel as well. So what do we have here? So this is going to be equal to the limit as k approaches 1 from the right of the natural log of k minus 1 minus the limit as capital N approaches infinity of the natural log of n. So as we already know, as the interior of the natural log goes to 0 from the right, this is going to go to negative infinity. As n gets arbitrarily large, the natural log also goes to infinity. So we have negative infinity minus infinity, if we wanted to think of this in terms of the hyperreal numbers, which is a negative infinite quantity. Whether you call it negative infinity or negative to infinity, it doesn't really matter. Nonetheless, it is a negative infinite quantity. So what does that mean? So that means this is definitely not a finite number. So that means the sum from k is equal to 1 to infinity of the natural log of 1 minus 1 over k diverges. And by the theorem that we stated earlier, that also means that the sum from k is equal to 1 to infinity of 1 minus 1 over k also diverges. And you can also, as a side example, if you want to investigate on your own, you may want to consider this product series and see if this converges or diverges. I'll leave that as an exercise to you in case you're interested. The next example I'm going to present is a very, very important theorem that was originally supposedly proven by Euler. So we're going to approach it via his approach on how he proved this theorem, and it's definitely one of my personal favorite theorems. So what we're going to do is we're first going to recall the Riemann zeta function. So recall that zeta of x is equal to the sum from k is equal to 1 to infinity of 1 divided by k to the power of x. And we're going to assume that this is true for any x bigger than 1. For all the other special values, we'll consider at another time. So what we're going to do is we're going to divide this expression by 2 to the x. So when we divide this expression by 2 to the x, what does that give us? Well, let's first off look at the expanded form of the summation. So zeta of x is going to be equal to 1 over 1 to the x plus 1 over 2 to the x plus 1 over 3 to the x plus 1 over 4 to the x, and so on. So when I divide both sides by 2 to the x, what do I get? So I'm going to have zeta of x all over 2 to the x is equal to 1 over 2 to the x plus 1 over 4 to the x plus 1 over 6 to the x plus 1 over 8 to the x plus so on. So what I'm going to do from here is I'm going to do zeta of x minus zeta x over 2 to the x. So I'm going to take this black equation and subtract this blue equation and see what I get. So let's write out our work before we jump any steps. That's going to be 1 over 1 to the x plus 1 over 2 to the x plus 1 over 3 to the x plus 1 over 4 to the x plus and so on, minus 1 over 2 to the x plus 1 over 4 to the x plus 1 over 6 to the x plus 1 over 8 to the x plus and so on. So as you may see on this right hand side, this is all multiples, so multiples of 2 to the x, if you may. So all the even bases. So that means all the even terms in this zeta expression are going to be canceled with their corresponding terms. So all of these will cancel because definitely there's all the even terms located in this infinite series. So we get the following expression. So zeta x, so we can factor out a zeta x out of the first and second terms of this. So we get 1 minus 1 over 2 to the x times zeta of x is equal to, so we're only going to be left with the odd terms in this first expression. So we're going to be left with 1 over 1 to the x plus 1 over 3 to the x plus 1 over 5 to the x plus 1 over 7 to the x plus 1 over 9 to the x, and so on. So that gives us this expression. So we have not built an infinite product series yet, but still on the right hand side this is an infinite series nonetheless. So now what I'm going to do is I'm going to divide everything by 3 to the x. So I'm going to divide everything by 3 to the x. So why am I dividing by 3 to the x? So the first number I divided by was 2, and now I'm going to divide everything by 3. So what is that going to do? So that's going to give me 1 minus 1 over 2 to the x times zeta x over 3 to the x is going to be equal to 1 over 3 to the x plus 1 over 9 to the x plus 1 over 15 to the x plus 1 over 21 to the x, and so on. So what I'm going to do is I'm going to take this blue equation and subtract this newly created equation. So this is going to give me 1 minus 1 over 2 to the x zeta of x minus 1 minus 1 over 2 to the x times zeta x all over 3 to the x. So that's going to give me what? So 1 over 1 to the x plus 1 over 3 to the x plus 1 over 5 to the x plus 1 over 7 to the x plus and so on. And then I'm going to take away 1 over 3 to the x plus 1 over 9 to the x plus 1 over 15 to the x plus 1 over 21 to the x and so on. So as you can see, 1 over 3 to the x will cancel. 1 over 9 to the x will be the next term in this term, so I'll just write that out here. So my 1 over 9 to the x terms will cancel. And all of these terms will cancel because this first series contains all of the odd base integers. So 15, 21, next would be 28. Those will all cancel out. So that means what? So I'm going to factor out a zeta x 1 minus 1 over 2 to the x, and I'm just going to be left with 1 minus 1 over 3 to the x in that first term. So I'm going to be left with 1 minus 1 over 2 to the x times 1 minus 1 over 3 to the x times zeta of x. And I'm going to be left with what? I'm going to be left with 1 over 1 to the x plus 1 over 5 to the x plus 1 over 7 to the x plus 1 over 11 to the x and so on. So by observation, all these base numbers, so namely 1 over a to the x, I'm going to write it in this form, a is not a multiple of 2 or 3. Or, namely, 2 and 3 are not factors of the base a. So then I'm going to divide by another number. I'm going to divide by 5. So 2, 3, and now I'm going to do it for 5. So I'm going to have 1 minus 1 over 2 to the x times 1 minus 1 over 3 to the x, 1 minus 1 over 5 to the x times zeta of x. So I'm going to be left with what on the right hand side? So I have 1 over 1 to the x plus, so I don't have 1, 2, 3, 4, 5, 6. Those are all multiples of 2, 3, and 5. So I'm going to be left with 1 over 7 to the x. 8, 9, and 10 are going to be gone. Then I'm going to be left with 11x. 12 wouldn't be there. 13 would be there because 13 is not a multiple of 2, 3, or 5. 14 is gone because that's divisible by 2. 15 is gone because that's divisible by 3. First off, 16 is gone because that's divisible by 2. Next would be 17, and so on. So all of these numbers, 1, 7, 11, 13, 17, are all going to be numbers that are not divisible by 2, 3, or 5. All right. So what would be next? So the next number that we would divide by would be 7. Then I'm going to divide by 11, then 13, then 17, then 19. So what I'm going to do is I'm going to divide by all multiples or all forms of p to the x, where p is prime. So there's a couple theorems that one should know already. So the first is there are infinitely many primes. This is very straightforward to prove by a contradiction example, but I'm not going to present that here. That's more for a number theory audience. And also, every number n bigger than or equal to 2 can be expressed as a product of prime numbers. So once I combine these two things and I continue the sieving process infinitely many times, and I can do it infinitely many times because there's infinitely many prime numbers, what I'm going to have is the following expression. So I'm going to have 1 minus 1 over 2 to the x times 1 minus 1 over 3 to the x times 1 minus 1 over 5 to the x, 1 minus 1 over 7 to the x, 1 minus 1 over 13 to the x. So 1, 7, oh, where's my 11? So 11, 13, 17, and so on, times zeta of x must be equal to just 1. Because 1 is the only term that is going to be located on all of these factored out expressions. All right, so how can we express this in a more compact manner? So we're going to let p of x, or we're going to let pk, be the kth prime number. And when I say the kth prime number, I mean that p of 1 is going to be equal to 2, p2 is 3, p3 is, so 2, 3, 5, 7, next will be 11, and so on. So the left-hand side of this expression is an infinite product. So we can rewrite this as the product from k is equal to 1 to infinity of 1 minus 1 over pkx times zeta of x must be equal to 1. So let's solve this equation for zeta of x. So I'm going to divide both sides by zeta of x, or the product, it doesn't matter. So I can rewrite this expression as pkx minus 1 over pkx. So once I do that, I'm going to divide by that product. So that's going to give me zeta x is going to be equal to the product from k is equal to 1 to infinity of pkx all over pkx minus 1. And this gives us a very compact form for the product of some rational expressions of polynomials and a connection with the Riemann zeta function. There's another alternative representation that one can write this as, and that's by multiplying top and bottom by pk minus x. Because all the prime numbers are not equal to 0, so you can always do this trick. So we can rewrite this as the product from k is equal to 1 to infinity of 1 over 1 minus pk minus x. So we get this very beautiful and intimate connection between the zeta function, the prime numbers, and also infinite products. So that's just a brief introduction of infinite products, some particular theorems associated to the convergence or divergence, and also a cute little example that connects infinite products, prime numbers, and also the Riemann zeta function. Hope you enjoyed.